to welcome everyone to what will be the last series of the Junior Seminar series. Today we have two outstanding speakers. Start with Christopher White, Dr. White we call him. He's a current candidate for Bachelor of Science degree in Electrical Engineering. First started chatting with Chris when he was giving me a hero full of passion about flying cars. His dream was to show that perpetual motion was possible and to design the next generation of futuristic car that can fly.
Was this successful?
He could never convince me. After many attempts at choosing a senior design about flying cars, Christopher reluctantly settled for building a radar. I mean that. Because he continued to come to me after many weeks after that, giving me more ideas about flying cars. So I suggested this project to him because I know that he likes to play with engineering toys, and he will definitely enjoy developing this project. And then he'll pick up tons of expertise in the area. So without any further ado, this is a great pleasure that I welcome Christopher White to the Junior Seminar series.
Okay, hello everyone. Thank you for coming out to John U. Free Seminar Series. Today I'm presenting on my radar system, which I built on MIT's laptop-based radar. So about a year ago, this time, go back to my outline. So the outline of my speak will be talking about my motivation, the theory behind radar, my methodology on how I accomplished the theory, the results and data I was able to get, and my conclusions and further work. So about a year ago, this time, I was a junior and trying to find ideas, like Dr. Coney said, and I watch a lot of sci-fi movies, and you see all these different ideas, and you're thinking, man, I can make this happen. However, I didn't really have all the resources to do that, so that's where I first started. What would I do? Trying to narrow down the ideas of the things that I was actually interested in that I could actually bring to life. This brought me to a website called sbir.gov, which is a site dedicated to site that the government uses, and different governmental agencies put up their requests for actual needs for like the Army or any other type of government need. And it's a place where different small business owners and entrepreneurs can try to address some of the issues that the Army or the government may need. And I chose a project from there, and I quickly realized that as an undergrad student, I really didn't have the resources to address a problem of such magnitude. But I decided to pick one, and I broke it down into different segments, and I thought that radar would be the best piece to investigate to address the bigger issue. I went online, and with the help of Dr. Freeze, I was able to find a small-scale, low-budget radar system that would be able to function like any other radar, but it's just able to be made in your own home. You can do it on your own time and that kind of thing. So radar essentially can be summed up with the phrase shout and listen. And as you can see here, what takes place is that there's a transmitted wave, and what happens is it bounces off of other objects, and that wave reflects back to the antenna. And then when it reflects back, you're able to take that data and predict position, velocity, and other aspects of whatever it bounced off of. So what takes place is that there's a carrier wave, and that carrier wave is modulated, whether in the frequency or amplitude, to be able to give you the results that you're looking for. But to be able to understand carrier waves and modulation, I have this example here. So what you can see is that there's a input signal, right, that is modulating these two sine waves here. So in AM, or amplitude modulation, what happens is the input signal modulates the height or amplitude of the carrier wave. in frequency modulation, the input wave here, the signal here, is modulating the frequency, the compression and expansion of the wave. So it has the same amplitude, but it just compresses it in the frequency. And this is what we use, this is exactly what takes place in AM and FM radio. And FM modulation is what was used here in the MIT platform. So here is a block diagram of what a CW Doppler mode looks like. And what CW Doppler means is that there is a single output wave from the transmitting antenna that has no modulation in the output signal. So what happens is there's a oscillator that creates the carrier wave, and it's a voltage regulated oscillator, and that passes through an amplifier, and that amplifier splits that signal to a mixer and to the first antenna, the transmitting antenna, which we call TX. And this is what it will look like here. So now we have this signal coming out of this antenna, propagating through the air, and we have that same signal going down to a mixer. Now, after it bounces off of different objects and it comes back to the receiving antenna here, we have a much lower amplitude signal that's out of phase. This is, you can relate this to shouting at the Grand Canyon, for instance. You'll shout, and what would happen is it'll take time for that wave to come back to you, but when it comes back to you, it's a lot fainter than the way you initially yelled. So the same exact thing happens here, where you send out this wave, it bounces off of objects, loses magnitude, and it comes back to you a lot less loud, for instance, in this case. So this passes through an amplifier, and after this passes through an amplifier, it goes to the mixer. The job of the mixer is to multiply the received wave times the sent wave. And the difference of two sinusoidal waves with the same frequency is the difference in phase. So that can be seen here in the green. So the red is the received, the blue is what was initially sent out, and the green is the information that we use to be able to determine speed, primarily for a Doppler. And in the frequency domain, we would see something that looks like this. It's a single spike, a single frequency with a particular magnitude. Now this is another example of what's taking place here. So we have the carrier wave, cosine omega t plus the phase, and that propagates through the air, and what we get back is the same wave with a different phase. But to demodulate this and get back the information that we want, we have to multiply by the sent signal, which was seen in the slide prior. And then that information, after you multiply the two of them, is the change in phase, or delta phi in this case. Now for FMCW, which is frequency modulated continuous wave mode, what happens is that we have a message that is carried upon the carrier wave, as seen in the slide prior. And it's going to be, that message modulates the carrier frequency, the carrier wave, I'm sorry. And that can be seen here. So now, the message, which is this, combined with the carrier wave, is sent through the air, propagates through the air, it bounces off of different objects, and you end up with the same information with on the receiving end of the radar. Then to get back this information, what we do is that we multiply it by the initial sent carrier wave, and we're able to get back what it is that we had initially sent. And also, in the frequency domain, it will look something like this. So this is our modulating wave in the frequency domain. And what happens is, after it's modulated, we end up with something like this. We have what we want here, but it also comes with two other spikes in the frequency domain. But after we get it back, what we want to do is we want to use the low-pass filter to be able to only get back the information that we want within a particular band width. And this is that band here within the blue box. This is the block diagram that was used in the MIT radar system. It comes with a modulator, and the modulator's job here is to do exactly what we just saw in the slide prior, is to modulate the carrier wave. The carrier wave is this oscillator here, and then after the oscillator, which produces our carrier wave at a very high frequency, we have an attenuator, a power amp, and then we have a splitter. So this entire signal chain here is all transmission. So at this antenna here, or cantenna in this case, because it's using coffee cans, at this cantenna, we're able to transmit the wave. After the wave propagates through the air and bounces off of different targets, it reflects a signal back, and this second antenna here picks that up. And the job of the second antenna is to pick it up, pass it through another amplifier, and the same way we saw in the slide prior, they multiply the descent wave by the transmitted wave, and that is a change in phase. And that passes through a series of amplifiers and a low-pass filters, as seen in the slide prior as well, to be able to get back the information that we want. The information that we want is within a particular band. So here it's within the 0 to 20,000 kilohertz bandwidth. So as you can see here, this is what I was able to make. A lot of work, a lot of sleepless nights, and a lot of dietary changes, but that's okay. But this is what I was able to build. So it's amazing to see that you can make a system with coffee cans, and it does the same exact thing as that of other systems out there. So in making the radar, there are different milestones or steps that needed to be tested as you went along. So for instance, the modulator had to be set at a particular output, a particular frequency, a particular wavelength. The oscillator had to be tested as well, and the low-pass filter and amplifier had to be tested. After I was able to verify that each individual part was working correctly, what I did was I made some guesses, some predictions as to what the results would be for different tests of the system overall. And I compared those predictions with what I actually got back. And I was able to, I first tested with a metal sheet, just a plaque of metal that we found in the lab. And it gave really good results, which I'll have at the end of the lecture here. And I was able to also do it with a car. I used my car, and I drove down. It was a Sachem, I believe. And I drove back up, and it gave some really good results, I think. So here's the modulator being tested. So the output of the modulator was a triangle wave, and we call this a ramp or a up chirp. And this up chirp is what we use to modulate the carrier wave to a particular frequency that we're looking to send. This was the low-pass filter and amplifier test. As you can see here, my input was this green sine wave here, and my output was the yellow. So you can definitely tell that within a particular band that the amplifier was working great, actually. Now for my results in Doppler mode, which is sending out a signal with a one frequency and it's not modulated. This is what I was able to get. This is what it looks like in the frequency domain. I was sending out a signal at 2.25538 gigahertz, which is very, 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 very high. And yeah, I was able to send it out successfully and get back data. This is a video of what the phase change looks like in Doppler mode. So what's happening here is that as my assistant's hand is being waved back and forth from the cans, you can see that there's a change in phase here on the screen. And it's only when there's something that's moving in front of the cans where you observe the change in phase. And I'll play one more time.
Why are there two cans there?
Well, one can is dedicated to transmission, one can is dedicated to receiving. Yeah. Most systems use one huge antenna like that. You'd observe it like air traffic control and just rotating constantly because they have a duplexer which will, the signal sends out something, as an antenna sends out a signal, it'll listen back before it sends out again. Has the capability of actually shouting and listening before it does another pulse. Okay, so these are the results I got from Doppler mode, which was primarily used for velocity. And this is what I got from shaking a piece of metal in front of the can tennis. So what we can see here is that, for one, it was only about 6 seconds or 5.25 seconds long. And shaking it, we were able to get speeds of about max, let's see here, 11 or was this 13 meters per second in velocity. The colors here represents the intensity of how well that the receive wave was able to be received by the receiving antenna. I'm sorry, how well the reflected wave was being received by the receiver. And this is the results that we got for shaking the metal sheet in front of the antennas for about 5.25 seconds. So we mainly were, right here in the 5 meters per second range for the majority of the time that we did this test. To be able to get data that didn't look as, how do you say, it didn't look as choppy, what I did was I increased the amount of time that I took my data for. So instead of doing it for 5 seconds, I did it for a minute, and this is what I got. So here we can see that for the amount of time that we took the test, we were in that same range that we were in prior to the other slide here. So for about 60 seconds of a lot of shaking, you can see that we were at about max 4 meters per second here shaking. We took a break. We just stopped altogether because it was pretty strenuous. But you can see here for the majority of the time that we took our data, it was about 4 meters per second velocity we're getting. This is in continuous wave Doppler mode. Now, when we went to frequency modulation, it got a little noisy here, but we were still able to get good data. So as you can see, as I was driving the car out, away from the antenna, you can see that my velocity was picking up, right? Because this is a time versus velocity graph. So my velocity as time went on was picking up, and eventually it lost me somewhere out here. But as I began to drive back, you can definitely tell that right here it began to pick me up again. And you can tell by the intensity, it's losing intensity. It's getting bluer and bluer and bluer and bluer and bluer. As I was coming back, it starts to get blue and tealish, green, yellow, reddish. So as I got closer, it was able to pick me up a lot better, a lot stronger. To test to make sure everything was actually working, what we did was we added a variable in there, which was a pause in time. So I drove back again, but this time I decided not to drive immediately as we started taking data. I waited about 5 seconds. And that wait can be seen here. As you can see, the data doesn't start until about, maybe 7 seconds, about 7 seconds in. Then you can begin to see that I began to drive out. And then once again, it lost me out here. And then as I began to come back in, the signal got a little stronger.
How far away were you when you lost the signal?
Ooh, Well, I was in the car driving,
Yeah.
so.
Did you get to the beach?
No, I didn't get to the beach. I drove down, I'm not sure what the cross street is at the stop sign. Yeah,
Driving, so
Driving, yeah.
less than that. Okay.
yeah, less than that.
And the equipment was mounted on something here back
Yeah,
in the car.
No, it wasn't in the car. It wasn't in the car. We took some lab chairs and 2 lab chairs, extremely long extension cable attached to another extremely long extension cable, and we made it work. We made it work. So it definitely works. You know, you can definitely see that there's a pause here. I didn't do anything. I just sat in the car in front of the antennas. And at about 7 seconds, I began to drive. You can definitely tell that the radar was picking me up as I was driving back and forth. So it just goes to show that this particular system is a low-budget, multifunctional, multi-purpose machine that can perform like that of any other radar, just at a lower scale. So I was able to reconstruct it, you know, from scratch. As you can see here, you know, there wasn't any fancy, you know, thing involved here. No kit that came that, you know, everything is nice package and all that kind of thing. So I was able to reproduce some results that the MIT team was also able to do when they first did this project. And in the process of doing this, I was able to learn a lot about radar, a lot about frequency modulation, a lot about wave propagation. And in the future, I look to be able to learn about linear frequency modulation. That's just a better way of taking data from a radar. I would like to thank Dr. Charvet, who is the designer of this system. He helped me a lot of back and forth emails, night, day, didn't matter. He was there to help me a lot. Dr. Cornely, who is, in my eyes, the master of radar, but that's just to me. Dr. Fries, he was the person who actually gave the idea initially to me and encouraged me to push forward. And Daniel Burley, he helped me a lot of fabrication, a lot of taking data, a lot of crunch work. And yeah. So any questions?
Any questions for Mr. White?
Yes.
So is this the kind of radar you would use in a flying car?
Well, in a flying car, we're going to have to, yeah, basically, you know, we'll use the same concepts, but we'll just adapt them to the car. That's right. Yes, sir.
Did the use of hot glue on the radar introduce any new complications in machine design?
The use of hot glue. Okay, so, okay, well, at one point in my building this wonderful project here, I applied some hot glue to a particular point, and after I did that, my data began to get very corrupted. So I would like to say yes, hot glue had a lot to do with this project. Yes. What's your Yoda?
Yeah.
Oh, I just think he's a wise man, so I just put him on. Yeah.
Mr. White, I noticed that all your velocities are positive. So is that just your magnitude of velocity? Would it be able to tell in general if you're going forward or backwards?
In Doppler, it is just the magnitude of velocity, which is why in a police radar gun, from what I understand, it takes the magnitude if you're going toward or away from the cop, in that case. So if you're going away from him, it'll tell you 75. If you're going toward him, it'll tell you 75. If you were actually doing 75, in that case. Yeah, always works in that area. Yep.
Any more questions for Mr. White? Okay, then, very good.